Hi everybody, welcome back to Statistics. Today we're in section 7.2 and we're talking about applications of the normal distribution. So last time we learned some of the properties of the normal distribution and we learned how to graph it, and today we're going to be talking about how we can use it. So I'm going to show you how to find and interpret the area under a normal curve, and I'm going to show you how to find the value of a normal random variable. And the big thing we're learning in this section is how to read the z-table. This is a big part of every statistics class. It's not hard, but I will tell you that the table looks a little intimidating. So give yourself time to learn this and absorb it, and you'll be reading that table like a pro in no time. Here we go. Now remember, in section 7.1, we learned that if x is a normally distributed random variable, then the area under the normal curve represents the proportion of a population with a certain characteristic, or it can also be thought of as the probability that a randomly selected individual from the population has that characteristic. So area can relate to either proportion or probability. But the question now is, how do we find an area under the curve? As long as we were dealing with the uniform probability distribution, we could just use the formula length times width. But you know the normal curve is not a rectangular shape. So how are we going to find the areas under the curve? Well, at first you might think maybe we could use a formula to find the area under the normal curve. You remember when we had the uniform probability distribution, we did use the formula for the area of a rectangle, and that's how we found those areas. But it turns out that because our curve bends, and it's not just a plain rectangle, the formula for finding the area under that curve is very complicated, and I don't think we want to mess with that. So your next thought might be, well, maybe we could get somebody else to calculate it for us and write down all of the areas in a table. Well, that sounds like a good idea, but then you realize there would have to be a different table for every possible mean and every possible standard deviation. And so that gets too complicated as well. But there is something else we can do. What we actually need to do is standardize our normal random variable. So here's what I mean by standardize. Suppose that the random variable x is normally distributed with a mean of mu and a standard deviation of sigma. Then we can calculate a new random variable that we'll call z. Z equals x minus mu all over sigma. You'll recognize this formula from chapter 3. This is our old z-score formula. And it turns out that if we have a random variable x that's normally distributed, then the z-scores will also be normally distributed, and the mean of the z-scores will be 0, and the standard deviation of the z-scores will be 1. And now this new random variable z that we have is what's called the standard normal distribution. So now what we're going to do for every normally distributed random variable that we have is we'll use z-scores to transform the random variable into a standardized form that we will call z. Now, because every histogram of z-scores has mu equal to 0 and sigma equal to 1, we only need one table. We can forget about having to have a different table for every combination of mu's and sigmas, because we can transform any random variable into z, and then we only need to have a table where mu is 0 and sigma is 1. And then we can use a z-table to find the area to the left of any z-score. Because the distribution of z is standardized, we call this the standard normal distribution. And the word standard just means that our random variable has been transformed so that mu equals 0 and sigma equals 1. Now, while we've got this diagram here, I want to show you one other thing. I know you remember that the inflection point occurs one standard deviation away from the mean. So for us, that means the inflection point occurs where z equals 1. And you also remember the empirical rule says that 99.7% of all values occur within 3 standard deviations of the mean. For us, that means that 99.7% of all z-scores will be between -3 and +3. So I think it's helpful for you to know that mu is always going to be at the center, and mu is 0. 1 occurs at the inflection point, and then 3 occurs out here on the edge, because remember, 99.7% of all z-scores will be between -3 and +3. So if we have 3 out here, 2 somewhere in between, so we can say 0, 1, 2, 3, and then on the left side, 0, -1, -2, -3. And so this is the way our graphs will always look, where we have -3 and +3 on the ends and 0 in the center. Now the table that I'm about to show you gives the areas under the standard normal curve for values to the left of a specified z-score like you see here. So what we'll do is we'll draw our standard normal curve, and we will have some z-score that we're working with based on the problem. And the table is going to help us find the area to the left of that z-score, which you see shaded here in blue. Here is part of the table. And now the whole table is in the formula sheet that I have posted for you in Canvas, but this is just part of it, and let me show you how to read it. Now remember that z-scores are always rounded to 2 decimal places, and this is why, because we have to be able to find z-scores in this table, and it only has 2 decimal places. So what we do is we find the first 2 digits of our z-score here in the left column, and then we find the third digit of the z-score in this top row, and wherever the row and the column intersect, that's the area we're looking for. So, for example, if I wanted to find the area to the left of a z-score of -2.15, we'd be talking about this area right here. What I do is go to the table and find -2.1 in the left column, and then I would go across until I got to the 0.05 column. And this number right here represents the area to the left of the z-score -2.15. So this blue shaded area here is going to be equal to 0.0158. That's how the table works. Now remember, the table can only tell you the area to the left of a z-score. So what happens if you need to know the area to the right of a z-score? Well, in that case, you can use the complement rule. Remember, complement means we subtract from 1. So 1 minus the area to the left of a z-score equals the area to the right of that z-score. But actually, it's kind of a drag to have to look up the area and then do a subtraction. So there is a shortcut, and the shortcut is this. Because the table is symmetrical, there is a shortcut way to find the area to the right. Instead of calculating 1 minus area to the left, what we can do is look up the opposite sign z-score. So if I need to know the area to the right of a z-score, I have 2 choices. My choices are look up the area to the left of the z-score and then do a subtraction, or look up the area to the left of the opposite sign z-score, and then I don't have to do a subtraction. So this is actually what most people choose to do in practice because it saves you a step. So let's think about this for just a minute. I want us to try a little experiment together. So first I want us to find the area to the left of z equals 1.33. Now I think it will be very helpful to you to make a habit out of sketching the graph first and draw the z-score on the standard normal curve first, and that will give you an idea of how big you can expect the area to be. So let's go ahead and sketch the standard normal curve, and we'll put a vertical line for z equals 1.33. Now because it's positive, I know it's to the right of 0. Remember, 0 is always right in the center. So positive 1.33 is going to be a little bit past the inflection point on the right side. I'll just put it there. And it says find the area to the left. So I'm going to shade the entire area to the left of z equals 1.33. Now that's pretty large. I can see that it's more than half of the area. So I'm expecting when I get over here to find an area that's larger than 0.5. In fact, pretty close to 1. So let's go down the left side to 1.3, and then we'll go across to the 0.03 column, and we see that the number is 0.9082. So that's going to be the area to the left of 1.33. And now let's calculate the area to the right of z equals 1.33. Well, you know the total area under the curve is 1, so this unshaded area is the complement of the shaded area. So if the area to the left is 0.9082, then this small shaded area over here on the right is 1 minus 0.9082, which is 0.0918. So the area to the right of z equals 1.33 is 0.0918. But now watch this. If we look up the area to the left of negative 1.33, then we'll come down here to the negative 1.3 line and go across to the 0.03 column, and we see that the area to the left of negative 1.33 is 0.0918, which is exactly what we found for the area to the right of positive 1.33. And here's what's going on. If we look at our standard normal curve, we know that the area to the left of negative 1.33 is 0.0918. And we found on the previous slide that the area to the right of 1.33 is also 0.0918. So this is happening because the graph is symmetric. In other words, it's the same on the right side as it is on the left. So for any negative z-score, the area to the left of that negative z-score is the same as the area to the right of that same z-score turned positive. So to find the area to the left of a z-score, we can just look up that z-score. But to find the area to the right of a z-score, what we want to do is look up the area to the left of the opposite z-score, and that will give us the correct area without having to calculate a complement. So to find the area to the left of a z-score, we look up the correct sign z-score, but to find the area to the right of a z-score, we look up the opposite sign z-score. Now, to find the area between two z-scores, all we have to do is find the area to the left of each one and then subtract the smaller one from the larger one. Here's how that works. Here's a standard normal curve, and I'm going to put two z-scores on it. And suppose we need to find the area between these two z-scores. So the way to find the area between z1 and z2 is to find the area to the left of z2, because that will be the larger area, and then we will subtract from that the area to the left of z1, and then all that will be left over is the area between them. So find the area to the left of z2 and then subtract the area to the left of z1. Now finally we'll get to do a few practice exercises where we'll get to practice finding the area to the left of a z-score, to the right of a z-score, or between two z-scores. So what I want you to do for each one is, with paper and pencil, sketch the graph yourself and then use the table to look up the appropriate area. So here we have z equals negative 2.45. So first I'm going to sketch a standard normal curve. Negative 2.45 will be here to the left of center because it's negative, and 2.45 is going to be quite far out, so I'm going to just put it there. And then I want to shade the area to the left of that z-score, and then I'm going to come to the table. Now you know the table tells us areas to the left of whatever z-score we look up. So go down to the negative 2.4 line and then go across to the 0.05 column, and you find an area of 0.0071. So the area to the left of that z-score is 0.0071. Now let's practice finding the area to the left of 0.43. So first sketch your standard normal curve, Positive 0.43 will be here to the right of center, but not quite to the inflection point. So I'll put it about there. And it asked us to find the area to the left, so I'm going to shade the area to the left. And now I can see from the shading that that is more than half of the curve. So I expect my area to be larger than 0.5. So I'm going to go down to the 0.4 row and across to the 0.03 column. And now I can see that the area to the left of z equals 0.43 is going to be equal to 0.6664. Now we're going to look at a couple where we find the area to the right of a z-score. So let's start by finding the area to the right of z equals negative 3.01. And again, it's always very helpful to start with a sketch. So let's sketch the standard normal curve. Z equals negative 3.01 will be almost all the way to the left. And it says find the area to the right of this z-score. So let's shade the area to the right. And you can see that that's almost all of the area. So we expect the area that we find to be very close to 1. So because we're finding the area to the right of negative 3.01, let's actually look up positive 3.01. So remember, whenever we want to find the area to the right of a z-score, we look up the area for the opposite sign. So if I go down to the line for 3.0 and across to the 0.01 column, I can see that the area for negative 3.01 is 0.9987. And so this area to the right is 0.9987. Now I want to caution you about a mistake that I see lots of people make when they show their work. A lot of times people will calculate a z-score and they'll find the correct area, but then they'll write this. They'll write negative 3.01 equals 0.9987. And that's just not true. Negative 3.01 is not equal to 0.9987. And I know what they're thinking. They're thinking that a z-score of negative 3.01 leads us to an area of 0.9987, and that is true. But that's not what they're writing here. This actually says that negative 3.01 is equal to 0.9987. Those two numbers are not the same number, and therefore we cannot put an equal sign between them. If you don't want to draw this in your show work window, and I understand why you would not want to try to draw this using the mouse, you can write it like this. You can just type out area to the right of z equals negative 3.01 is 0.9987. This is acceptable, but to put an equal mark between these two numbers like this is not acceptable. And now let's find one more area to the right. So this says find the area to the right of z equals 1.59. Again, always start with a sketch. Even if you don't draw this in your show work window, please do sketch it on a piece of paper. I always do this myself when I'm working these problems on my own. It just really helps to have a visual cue to help you know whether your answer should be more than 0.5 or less than 0.5. So here we have z equals 1.59. Now that's positive. So my z-score line is going to be on the right side of center, and it's going to be just a little bit past the inflection point. And so I'll put it here and say that z equals 1.59. And now if I shade the area to the right, I can see that this is less than half of the area. So you know, if you did forget what you were doing for a minute and you accidentally looked up z equals positive 1.59, you would see from the answer you got that it's too large, and you would know that you had done something wrong. So that's why I always recommend drawing this sketch. Now remember, we're finding the area to the right, so we need to actually look up the opposite sign z-score. So here I have the part of the table where we can find the negative 1.5 line, and then I go across to the column for 0.09, and that's right here. So the area to the right of z equals 1.59 is 0.0559. And now we're going to find the area between two z-scores. And again, as I've said several times, we always want to start with a sketch. So I will sketch my standard normal curve, and then I'll draw a line for negative 2.04 and a line for positive 2.04, and we want to find the area between them. So that's what I've shaded here. Now remember, the way to find the area between two z-scores is to find the area to the left of the larger one and subtract the area to the left of the smaller one. So now I can say the area to the left of 2.04 is going to be 0.9793, and the area to the left of negative 2.04 is going to be 0.0207. And now to find the area between these two z-scores, we say 0.9793 minus 0.0207 equals 0.9586. And that makes sense if you think about the empirical rule, because remember, according to the empirical rule, about 95% of the observations will be within 2 standard deviations of the mean. So we should expect about 95% of the area between z equals negative 2 and z equals positive 2. These two z-scores are not far from negative 2 and positive 2. Therefore, the area is not much bigger than 95%, just a little bit. And now let's find the area between z equals negative 0.55 and z equals 0.0. Start with a sketch as always, and then we'll draw a line for the z-score of negative 0.55. That's going to be to the left of center just a little bit. And the line for z equals 0.0 is going to be right here in the center. Here's the area between them. Now to find this area, we'll look up the area to the left of 0.0, and that's going to be 0.5, of course. And then we'll look up the area to the left of negative 0.55, and that's going to be 0.2912. So the area between those two scores is 0.5 minus 0.2912, which is 0.2088. So the area between these two z-scores, again, is 0.2088. Now here's one that's worded a little differently, but I think when you see it drawn, you'll know exactly what to do. This says find the area to the left of negative 2.00 or to the right of z equals positive 2.00. So start with a sketch. Here's the line for z equals negative 2.00, and here's the line for z equals positive 2.00. The area to the left of negative 2 is this little slice here, and the area to the right of positive 2 is this little slice here. So if we want the total area, I think you can probably see that we'll have to add these two areas together. So let's start by finding the area to the left of z equals negative 2.0. So we'll come down to the line for negative 2.0 and go to the 0 column, and the area to the left of negative 2 is 0.0228. And because this z-score is the same as that one, the area to the right of positive 2 is also 0.0228. And so now to find the total area, we just say 0.0228 plus 0.0228 for a total area of 0.0456. And here's one more like that. This says find the area to the left of z equals negative 1.56 or to the right of z equals positive 2.56. So let's start with a sketch as usual. The line for z equals negative 1.56 will be here to the left of the left inflection point just a little bit, and the line for positive 2.56 will be out here close to 3. So the area to the left of negative 1.56 is this little slice, and the area to the right of positive 2.56 is this little slice. So looking at the table, the area to the left of negative 1.56 is going to be 0.0594, and the area to the right of positive 2.56 we'll have to find by looking up negative 2.56. So we go to the negative 2.5 line and go out to the 6 column, and we find the area to the right of 2.56 is 0.0052. And then to find the total area, we just add these two areas together. So 0.0594 plus 0.0052 gives us a total area of 0.0646. Now we are finally going to get to do an application problem. Now that we know how to read the table and how to find the area we want, let's actually use that to solve a problem. So this says a pediatrician obtains the heights of her 200 3-year-old female patients. The heights are normally distributed with a mean of 38.72 inches and a standard deviation of 3.17 inches. Use the normal model to determine the proportion of 3-year-old females that have a height less than 35 inches. So because we know that the heights are approximately normally distributed, we can use the area under the standard normal curve to help us solve this problem. Let's start by transforming 35 into a z-score. So 35 is an x value. It's a value of our random variable. And to find the z-score, we say z equals 35 minus mu divided by the standard deviation. And that gives us a z-score of negative 1.17. By the way, you may already know this, but I just want to make sure. Anytime we have an x value that's less than the mean, that will give us a negative z-score. And an x value that's more than the mean will give us a positive z-score. So before we even calculated anything, I knew that this value was less than the mean, and I knew we were going to come up with a negative z-score. Okay, so here we have our z-score of negative 1.17. And now we can draw our standard normal curve, and we want to draw a line for negative 1.17. Of course, that is to the left of center. I'll put it out here somewhere. And since they asked us to find the proportion of 3-year-old females who have a height less than 35 inches, I will shade the area to the left because that's where the less than heights are going to be. Less than is to the left, greater than, of course, is to the right. So let's shade that area to the left of negative 1.17. The area under this portion of the curve is going to be equal to the proportion that we're looking for. So now let's look at the table and find the area to the left of negative 1.17. And that's going to be here. And so we find that the area to the left of z equals negative 1.17 is 0.1210. And that means we can say that the proportion of 3-year-old female patients whose height is less than 35 inches tall is approximately 0.1210. Here's a similar example, and this is example 2. It says for the pediatrician presented in example 1, find the probability that a randomly selected 3-year-old girl is between 35 and 40 inches tall. That is, find the probability that x is between 35 and 40. Well, the way to do this is to transform both of these into z-scores. So for the x value of 35, we already know that z equals negative 1.17, and we calculated that on the last slide, so I won't do it again. But for 40, if x equals 40, then z equals 40 minus 38.72, all over 3.17, and that's a z-score of 0.41. So now let's sketch that on the standard normal curve. The line for z equals negative 1.17 is going to be over here to the left of center somewhere, and the line for z equals 0.41 is going to be on the right side, not quite to the inflection point. And we want to find the proportion of 3-year-old girls whose heights fall in between these two z-scores. So what we'll do is find the area to the left of z equals 0.41 and then subtract the area to the left of negative 1.17. So according to the table, the area to the left of z equals 0.41 is going to be 0.6591, and the area to the left of negative 1.17 is going to be 0.1210. And so evaluating that subtraction, we find the area between those two z-scores is 0.5381. And so we can state our final answer this way. The probability that x is between 35 and 40 is equal to 0.5381.